today I'm going to talk about energy, actually. So what I wanted to talk about is new ways of converting solar energy. And I think one of the exciting things about this field is that we have some well-established technologies which are going forward for high efficiencies and lower costs, but there are also opportunities to innovate new devices, new structures that could ultimately be even more efficient. So what I want to look at is solar power conversion. And if we just break this down very simply, as you guys have seen, there's actually two general ways to do this. You can do solar thermal, where you take all the light from the sun, you use it to heat something up really hot, and then you use it just like you would like a coal furnace or something like that. It's just a heat source. Okay? So it's not terribly efficient use of the energy, but it uses all of the energy. On the other hand, you can do photovoltaic conversion, where you're going to take just a section of that solar spectrum and convert it fairly efficiently into energy. But then you also have this whole other section of the spectrum that you don't use and you waste, right? And so if you look at it, on balance, they're roughly the same efficiency, about 20% up to 25%. These are very typical for these two combinations. Now, let me give you another question. How efficient are fossil fuels, right? Coal, natural gas, right? How efficient is a coal plant? Anyone know? 35%. Okay, yeah. 33, 35 with the latest generation. All right. Then, how efficient are natural gas plants? Well, they're over 55%, and the latest GE one, they claim up to 60% efficient. That's pretty good. Now, what's the difference between the two? Is natural gas somehow magically burning hotter and getting much, much better?
Bottoming cycle.
Yeah, bottoming cycle. So in this case, you're going to do two cycles together. Combined cycles are what they called. And so you're going to take that natural gas, it expands, that drives a turbine, you get energy. Then you take that heat from that gas, and then you boil water, and that drives a turbine, and you get energy. Okay? And so you're really trying to use that energy twice. And that's how you can get to remarkably high efficiency, even from basically the same kind of power source as a coal plant. So the obvious parallel then is, how do you do combined cycles for renewables, say solar energy? So you'd really like to do a combined cycle as well. Combine these two together to get higher efficiency from the same amount of initial energy. So one simple way to think of this is just take your sunlight, hit a photovoltaic cell, get some electricity out directly, and then take all the waste heat and dump it to a thermal engine. Now, if a photo cell is 20% efficient, that means it's 80% inefficient, right? So it's actually a really good heater. 80% of that energy is going into heat. And so you'd like to be able to take that heat and dump it to like a thermal engine, like a Stirling engine, or even just a simple steam engine, and drive that, convert that waste heat into useful energy once again, and then dump it down to even lower temperature. Makes sense, yeah? All right, sounds great. Okay, so let's just do a very simple analysis of how a combined cycle would work in terms of efficiency. And let's say you would take your sunlight, go to 600 degrees C. That is a typical steam engine, a little bit higher, but fair enough. 25% efficiency of a PV stage, then you get 25% of your initial energy out. Then you take 75% of that energy and you dump it down to the thermal process. It's also roughly 25% efficient. So you get 19% out of that bottoming cycle for a total of 44% efficiency. That's not bad. So this approach actually has some really interesting advantages over typical, very, very high efficiency silicon cells, or even photovoltaics. You're taking two cycles which are both pretty good, but not amazing. These don't have to be the best devices ever to get to 44% efficiency. They can be pretty good with what we have today. And if you combine two things which are pretty good, as we know, the rate at which things break down and the cost at which there is to fix them goes up with how ideal these structures are, right? Fixing a Lamborghini is a lot more than fixing your little Beetle, right? And so same thing is true in solar energy conversion. And so you'd like to do this with two cycles which are good but not amazing, and then coming out with very, very good performance in the end. That's very attractive. So Why haven't people done this? I'm obviously not the first person who's realized that if you could do this for renewable energy, it would be a great thing, okay? So what's the problem here? Well, if you take this sunlight and you dump it to a PV stage, that PV stage has to operate at a high enough temperature that it can actually be used for thermal conversion. That's about 600 degrees, all right? So how do photovoltaic cells work at 600 degrees? Good, good. Badly is right. In fact, about 0% efficiency. The fundamental physics of how p-n junctions work say as you go up, your efficiency goes down linearly. And by the time you get to 600 degrees, you get nothing. Otherwise, we wouldn't be having this discussion. These would already be out in the field and be the cheapest, most effective renewable technology out there. Okay, so the question is, can you make something that would look like that based on a p-n photovoltaic? And the answer is no. You can't do it. As I said, p-n junction photophysics, the basic physics of that mechanism say you can't go higher temperature and still get more efficiency. It's going to go down the higher you get. You can go to different materials with larger band gaps to go to slightly different higher temperatures, but you can't go to 600. Okay, so what do you do if you want to do some combined cycle like this? And this is where we started in the energy business. My group was not traditionally an energy group. But we came in and we said, look, we have some unique technologies, which we'll kind of discuss a little bit later. Where can we make an impact in this field? And I think this is a great question for engineering. You've identified something where if you could make a device that would act kind of like a photovoltaic, but at 600 degrees C, you could make an impact on the economics of a very important region, right, in renewable energies. This is a great challenge for engineers, right? I'm telling you, it's great. If you could do it, just give me something that looks like a PV, operates at 600. All right? And that's where we came into it, and seeing that as the central challenge to make a new device that would be highly, highly efficient. And so what we did is take a look at processes that do work at very high temperature. In this case, thermionic emission. Okay? So thermionic emission is actually more familiar to you than you might expect. But basically, it's similar to boiling water. You input energy into water, and you boil the water molecules from the liquid state into the gaseous state, and they come out. All right? You can do the same thing, actually, with electrons. If you put in enough heat, you'll give them enough energy to actually come out of the solid and boil off the solid surface. Now, this obviously does not happen at low temperature, but you go high enough temperature, it will actually happen, generally above 1200 degrees or so. Quite robust. It's kind of like the ultimate Carnot engine in that the working fluid here is not water or anything like that. It's actually electrons. And so it's quite robust if you can get it going. And I'm going to show a few diagrams that look like this. So let me explain them very quickly. This is called an energy level diagram. What I'm plotting here in the horizontal axis is some spatial coordinate. So this is distance or something like that. And in the vertical is the energy of the electrons. And so normally at room temperature, the electrons would have kind of a uniform distribution shown in the gray. As you heat them up, there's going to be a Maxwell distribution of electrons at higher energies, just hotter thermal energy. You go hot enough, these will cross what is called the vacuum gap, or the vacuum energy, not the vacuum gap, sorry, vacuum energy. Above that, electrons are allowed to come off the surface, so they can boil off. So you get hot enough, you overcome what is known as the work function, which is the difference between this level of the electrons at low temperature and the vacuum level. You jump over that, electrons come off. All right, so where have you seen thermionic devices before? Well, you've seen them in vacuum tubes, actually. So in these cathode ray tubes, they will actually use a little barium target, heat it up with a tungsten filament. It'll get to about 2,000 degrees and emit tons of electrons. Where have you seen this before? Is this a really outlandish technology? Well, maybe you guys haven't seen this before, but for the older members in the audience, this is actually a fairly familiar sight. This is a cathode ray tube television, CRT, yeah? And so this is basically just an electron beam that heats up to a couple thousand degrees and then sprays electrons at your face and then rasters them on the colored screen. That's how it works. So this is very common technology, actually, whether you know it or not. Okay, so how do you do energy conversion using thermionic emission? Well, what you do is you take one metal that gets really hot, emits these electrons, and then you have another metal a little ways away that's generally colder to collect those electrons. And so you get electrons coming from the hot metal, jump up to this vacuum level, down to the anode. You usually want to have this spacing, called the vacuum gap, as close as possible, and you want it to have vacuum, so nothing in here. So this is generally pretty good, which is why it's a vacuum tube. Fairly simple here, all right? OK, now, a couple important points. One is if this work function is very large, it requires very high temperature to get those electrons out. So you'd like that to be as low as possible so you don't have to go to really high energy. The second thing is that the voltage you get out of the system is actually the difference between this cathode work function and the anode work function. So in fact, you want this to be as large as possible to maximize the voltage out. So you've got a trade-off immediately, that you want this to be big, and yet you want it to be small. And the outcome here is that the voltage out is generally very low, about 100 millivolts, maybe about a seventh or a fifth of what a normal silicon PV cell is. So these are not very efficient devices at all. How would you increase that output voltage? That's what we came down to. So this is great, but it's really ineffective. All right? So if we look at this band diagram, what we're doing is we want this cathode work function to be really large, this to be relatively small, so we get a big V out. All right, that's the goal. So how do you get electrons even higher? Well, obviously, you can heat them up even more. How else could you do it? That was the question that we faced, all right? So what we decided to do is look at that and say, well, by the power of PowerPoint, I can just take that distribution of electrons and shift it up, yeah? Grab it, move it. There you go. Now these electrons are over the vacuum level. These will emit, and then you'll collect them, but still have the low temperature level down there. All right? So how do you make that in reality? OK. So in fact, this is actually a very well-known structure for anybody in electrical engineering. This is merely a semiconductor, just like you would see in a solar cell. So if you start with a semiconductor, you hit it with light, then it excites the electrons from down here up to this conduction band. Now they're in this upper level, and due to the heat of the material itself, they will also have a distribution, but now it is starting from the conduction band level rather than down here. And so now you can collect all of these electrons very easily. And you can show that the number of electrons that you can get at room temperature is about 1 billion times higher in this process with a silicon device than it would be with a thermionic device. It's a big enhancement because photon energies are very, very large compared to thermal energy. Right? Room temperature thermal energy is something like 25 milli-electron volts. It's almost nothing, very small. A low energy photon is about 2 eV, a red photon. And so that is much, much larger. So you get a big, big boost due to the photo effect. And so you can think of this as kind of a two-step system where you're going to come in with photons, excite those electrons in here. This whole top cathode then will be very hot, heating the electrons up, which happens at about 10 picoseconds. So it's fairly fast. And then emits to a cooler anode. So this could actually be a very effective conversion device, which we call photon-enhanced thermionic emission. So it's thermionic emission plus the photons to give it that extra voltage. And essentially what you're doing is giving yourself a photocell and then also getting this thermal energy out. So you're converting both photon energy and thermal energy at the same time. And this was recently published a little while ago. And it's, I think, a really exciting avenue to create high-efficiency energy. Now, what would this actually look like? Well, in the simplest implementation, it would basically be 2 wafers stacked on top of each other where the sunlight would come in, excite them, and then be collected at the anode. So this would just be kind of a vacuum flange kind of thing, maybe 8 inches in diameter, a couple inches deep. And you can imagine bolting these things onto, say, Stirling engines or other thermal collection systems, which already have focusing mirrors. So you have all the infrastructure there to actually put light onto these things. And this would basically be combined with this process. More advanced structures could be using MEMS, micro-electromechanical processing, to make a chip that has everything packaged in the chip itself. So you wouldn't actually have the external vacuum or anything like that. It would just look like a wafer with some fancy coatings on it. OK, what about the efficiency? So we went through and we calculated what it could do. And what you see is that the peat efficiency in the solid lines here can actually beat that of a single junction photocell, an ideal single junction photocell. And so we see that at 100x concentration, you want as much light as possible, you can get about 35%. 1,000x, you can get over 40%. And at 3,000x, you can get almost 50%, about 48% efficient, which is better than the ideal single junction solar cell at the same concentration. So that's actually really promising. It can beat a single junction solar cell. And the reason for that is because part of the energy comes from photons and part of it comes from heat. OK, so this was a new idea, surprisingly enough. Nobody had described this, even though the thermionic emission has been around since 1880. So it's been known since this university has been established. And then photoemission has also been well known, also about 1900. So does it exist? Well, we decided to test it with this gallium nitride material. We put it into a big vacuum chamber, heated it up. Here you can see the sample heating. And then we're going to hit it with light. And the big, we did a number of experiments. The one that kind of kicks it here is that we come in with two different wavelengths of light, some blue light and green light. And neither of these is energetic enough to get electrons off the surface. And yet, you see that they come out with more energy off the surface than they went in. And so they're actually picking up this thermal energy. In the case of green light, you're picking up half a volt of thermal energy. That's pretty good. So you can basically take whatever your photocell voltage is and add half a volt onto it using this process. That's very exciting. We also showed that efficiency increases nicely with going up in temperature. This is fairly low temperature on gallium arsenide. But you can increase the temperature and then get more efficient electron emission. So that's what you're looking for. Our initial report was like 10 to the minus 4 in terms of quantum efficiency. So is great proof of principle good for your first device? Not so good for actual conversion. We've since made some better devices, gone up to about 2.5% quantum efficiency, and are trying to improve that now. And we have a pretty good idea of what to do next. OK, one of the nice things about this peat idea is that it would basically not be a standalone. You're not going to compete with something like bright sources, power towers. You're actually going to add on to them. So this is going to be an additional device that makes things more efficient. And if you look at the theoretical efficiency for a tandem, first the peat, then going to a just 30% Stirling engine, something like that, peat alone might be about 40% at 1,000x. With the tandem, it can be well over 50%, 55%. So theoretically, it could be very, very exciting. We're not efficient enough yet, but that's why we do research. If you look at what's required to make peat cost competitive, we used a lot of the solar cost modules from NREL and estimated how efficient we'd need to make this process be to be economically viable. And really, if we're going to compete with natural gas type prices, we need the peat to be 15 to 20% efficient. Gives us about 40 cents a watt additional. That's actually pretty exciting. We don't need it to be the theoretical maximum efficiency. I'll tell you, if you need your device to be the theoretical maximum efficiency, it's unlikely to ever be practical. This is something like a third, which is much less than what silicon solar cells. They're theoretically about 34% efficient. They are roughly 24%. Right? So this is pretty good that we can be a third of the theoretical maximum and still make an economic impact. Very exciting for practical applications. So take-home messages, I think, one, look for new ideas. Combined cycles, I think, are a really exciting thing in renewable energy. And people have thought of some ways to do it, but there are more out there, I'm sure, that people can discover, and maybe easy and practical as well. Peat is one way to do this, to make a combined cycle, combining thermal and photon energy. And then reasonable peat efficiency really could make an impact by combining it with things like power towers and Stirling engines. OK, so that gives you kind of an overview of our research in the energy area. And I'd be happy to take any questions.
To get to that high temperature, you have to collect solar radiation from a larger area, right?
Mm-hmm.
And concentrate it. So
yeah.
I'm wondering, simple back-of-the-envelope calculation, for a given acre of land, which one would produce more? Let's assume that it's 44% efficient, and then other solar panel is, let's say, 18% efficient for market rate. So which one would produce more energy per acre of land than?
Oh, well, if you're looking at per energy, that percentage is the energy. So 44% will always be 18%. I think the other question is which will cost more, which has also the cost of all these structures in. If you can get this to 44%, it'll beat silicon solar hands down.
For a given acre of land, right?
Oh, yeah. So you can imagine that these guys are already being built by Tessera and some others, and eSolar are building power towers. They're not quite cost competitive with gas, gas right now, but they're not too far off. And so if I can say to you, all right, you've already built this thing, I can give you a module which will increase your efficiency by 75% and cost you less than a third of what it costs to build this. It's a win-win. And you can imagine that if you're designing a new plant, then if I can almost, let's say I just double the efficiency, going from 20% to 40%, you would need half the land you'd need before. And for environmental and cost purposes, the cost per square foot is a big deal. So I think you really want to go to higher efficiency.
Is your 50% maximum, is that including the kind of like a Stirling engine or something recovering the rest of the heat? Or
yes, yeah. With 55% efficiency, we, in the Tandem cycle, assumes that you'd have a Stirling engine. If you have 3,000x concentration, you can get to 50% by the peak by itself. But 3,000x is pretty high concentration. It requires good tracking. Most of these kind of things are between 500 and 1,000x solar concentrations right now, and so that's kind of the range that we're homing in on.
So thinking in terms of combined cycles a little more, is it possible to also use thermoelectric devices in tandem with?
Sure, yeah. People have been very interested in doing thermoelectrics. Unfortunately, they're just not efficient enough. If you can make it really efficient, yes, absolutely.
Can I think of your device as a Schottky diode rather than a...
Yes, and so we have definitely considered making this as a Schottky diode. The issue turns out to be that Schottky diode is basically the same thing where you have a barrier and then you get the electrons jumping over, but it's all solid state. You don't have this vacuum gap in the middle. The problem is that both sides are at the same temperature, or very nearly so. And so you get as much reverse current as you get forward current. In fact, you get more reverse current than you get forward current. And so at the limit, the best that you could do is basically the PV voltage out. And so it's not a win.
As a follow-up, how do you keep one side hot and one side cool? Because wouldn't the hot side emit phonons that heat the cool side?
Well, if you have a vacuum gap, they're not in direct connection. So it's just black body radiation between them, which isn't terribly efficient at converting energy. And then the second thing to remember is we're going to have a bottoming cycle on it. We're going to have it boiling water or something like that on the bottom. And so that bottom temperature is set, and then the top one can get much hotter.
So in terms of having these semiconductors operating at 600 degrees Celsius, what's the lifetime expectations that you have?
Yeah, it's a good question. People don't normally think of operating at 600 degrees C because it's not good for conventional ICs at all. We don't know. The bulk materials are going to be okay, but what we're concerned about is a surface process, these electrons coming off the surface. That's a much less understood and known process at these higher temperatures, so that's something we need to find out.
Do you need external heating sources to heat the cathode too?
No. Yeah, so it's pretty remarkable how hot you can get things just with a little panel. So we have a Fresnel lens that's about that big, and we can melt a copper block in a few seconds. So solar energy is plenty hot. It's amazing how hot you can get things. And so in fact, you have to worry about heating it up too much rather than the reverse. Yeah.
When you talk about your current efficiency and the theoretical efficiency, what are the main areas that need to be worked on to get that higher?
Yeah, and so the actual efficiency is about, the quantum efficiency is about 2.5%. There are three things that make it less efficient. The number one is going to be surface recombination, that electrons that don't have enough energy to emit hit the surface and recombine due to defects, dangling bonds, all kinds of things at the surface. That's the number one. And that's actually by mitigating that, that's how we went from 10 to the 4 to 2.5%, right away. And so that's the number one. And these kind of things have been well known in the semiconductor industry for a long time of surface passivation. We just have to figure out how to do it at a high temperature. The other big thing is going to be absorption. You want to make nanostructured films to try to absorb all the light in a region really close to the surface, so it's fairly likely that those hot electrons are going to get to the surface before they recombine. So there's the two things that we're working on.
Is it more difficult to absorb the photons when they're so concentrated?
When the photons are concentrated. No, we're not getting high enough to get nonlinear. So if you really blast things with light, you'll actually deplete the number of electrons, and then your absorption coefficient will go down. That's quite a bit higher than, that's more like 10,000x concentration. Yeah, the linear regime thing.
Is expansion and contraction going to be an issue for the lifetime of it?
Absolutely, yeah. Anytime you talk about solar, even low temperature solar, expansion and contraction is always something that you have to worry about. That really does affect lifetime. So we have to think about ways to have these so you don't clamp them in, for example. You allow the wafers to expand and contract naturally. And we have a couple ways to do that right now. But absolutely, you must consider that. Great. Thanks very much.